Next method that we're going to look at is a general technique called the recursive method. And it's an old method that is effective. And we'll take a look at a modern rendition of it. So what we do is we start with a specification, which usually and often they're just recursive definitions of a combinatorial class. And what we need to do is pre-compute some probabilities, and I'll give a couple of examples. And then from those things, we can pretty much directly generate a recursive program that will create a sample. We've already seen an example of this, and I'll come back to it in a minute. That was in A of A Lecture 6, we talked about generating random trees, and I'm going to revisit the details of that a little bit later. So this is from Lecture 6, and it's a recursive program. Generate calls generate, and we're going to look at this program again later. Okay, here's really a simple illustrative example. Random bit strings with no 0, 0. And when we introduced analytic combinatorics and analysis of algorithms online lecture, this was one of the examples that we used. So we can write a formal specification based on this informal description of what an n-bit string having no 0, 0 is. Class of bit strings with no 0, 0, it's either empty or it's 0, or it's a bit string with no 0, 0 followed by a 1, or it's a bit string with no 0, 0 followed by a 1, 0. That's the spec. Now in order to generate a sampler from this spec, we're going to need to calculate a probability. And the probability we need is, what's the probability that the string ends in 1 versus whether it ends in 1, 0. And we're going to use that to choose which of those two aspects of the generator we're going to use. And back when we looked at this in the analysis of algorithms course, we did these calculations. So the number of strings in the class is about phi to the n. The number of strings that end in 1 is about phi to the n minus 1. And the number ending in 1, 0 is about phi to the n minus 2. It's Fibonacci numbers. So therefore, the probability that it ends in 1 is 1 over phi. That's our pre-computed probability in this case, and it immediately leads to this recursive program. If our length is 0, we return the empty string. If our length is 1, we return 0. Otherwise, we generate, we do a Bernoulli random test, a coin flip with probability 1 over phi. And if we get heads, then we generate the string of size n minus 1 and add a 1. Otherwise, we generate one of size n minus 2 and add a 1, 0. That's a recursive program that's going to generate a random bit string having no occurrence of 2 consecutive zeros. And that'll work in linear time for large n. It's a fine way to solve this problem in this case. So we can do it for binary trees. That's the example that we talked about before, and I'll just go through the same process again. We talked about, I mentioned, we talked about it in terms of the symbolic method in analysis of algorithms, and we also talked about generating random trees in that online lecture. So in this case, the pre-computed probabilities are a lot more complicated. The probability that the subtree sizes are k and n minus k minus 1 are given by this formula. That's the number that is size k, the number of size n minus k minus 1 divided by the total number. We need that probability, but given that probability, and that's held in an array called cat n, we can just call our discrete random number generator. This gives all the possibilities for all the subtree sizes to get our subtree size, and then to get a tree of size n, then we just, that's our root, create the new node, and then we generate a left subtree with k nodes and a right subtree with n minus k minus 1 nodes. Again, a very simple recursive program that derives automatically from the recursive spec. Binary tree is either empty or a node in 2 binary trees. but we do need these probabilities. And so, boom, we can get a tree of size 100 this way, and that's what we did in the analysis of algorithms course. So the whole basis for it is that we need these pre-computed probabilities. This can be handled with a, well, we call it a dynamic programming solution. We just build it up. If we have it for n-1, we can go through and figure it out for n. We keep a two-dimensional array, and we discussed this code in the analysis of algorithms course. The key thing is, in this case, well, number one, you can use the same technique for all kinds of trees. Basically the same kind of idea, more complicated program. And actually, you can it turns out you can use the same technique for any constructible combinatorial class, and I'll come back to that. But the caveat is that it's going to require a lot of time and space in general. And in this case, it's quadratic. We have nested for loops. So that's going to prohibit us from generating huge trees. Now, but still, there was this paper published in 1994 was a very important landmark by Flageolet, Zimmerman, and Van Cutsem, showing that it really, a lot of these ideas were discussed by Wilf and Nienhuis in that 1975 book. But the combinatorial constructions that we use today were just coming into use. And this paper actually proved theorems that said that you can, with pre-computed tables of size proportional to the size of the structure, and actually with n log n time complexity, you can generate really any decomposable structure. So this is a random 0, 2, 3 tree produced according to these ideas. A very, very significant paper. And it's the basis for full implementation that has been used for decades. And in fact, there's multiple industrial strength random sampling packages that are built from this idea. So the Flageolet and Salvi paper, Computer Algebra Libraries for Combinatorial Constructions, 1995, they talk about the program called Lua, which now is the basis for Construct in Maple, that automatically takes a spec and compiles it into a random generation method. And that's been used for decades within Maple. I mentioned the random genomic sequence application, and this is another one that is an open source package for generating random genomic sequences and structures based on the recursive method. And soon modern implementation is going to be available in Sage and Python. And the bottom line is that with the recursive method, we can automatically handle any constructible combinatorial class. Now, we're not going to go into full details of these implementations because there's an even more powerful idea that we want to consider in the next section. So here's the context. So with the recursive method, we get an automatic uniform sampler for any constructible class, but we have this problem that the pre-processing can be excessive in both time and space in general. Doesn't really scale. So with the recursive method, we have extendable. That is, we can do any extensible. We can do any combinatorial class, but it's not always scalable. The trees we get are relatively small. With Remy's algorithm, we were able to get huge trees, but it's not extensible. And really, what we want to look at in the next challenge is, can we get big trees of all types and other combinatorial objects of all types in an extensible manner? That's what we want to look at next. Scalable and extensible uniform samplers.